Okay, so on example one, we had that time interval shrink to zero or get as close to zero as we could for the time being to find the instantaneous velocity. Now they're wanting us to talk about a graphical representation of that. So we have average speed or average rate of change is total distance d, which would sometimes they use s there, divided by the elapsed time period t. Graphically, it's the average speed or rate of change is the slope of the secant line. I'll draw that in just a second. And the average is, they call it AROC, change in the distance over the change in time. So it says sketch the secant line. All right, so let's come over here and let's have it do this for us. I think it's already, there we go. It's already online. So let me see if I can draw this pretty good. Look at there. Not bad. Okay. Pretty happy. You could probably do a better job than that on your paper, but I'm pretty happy with that. All right. So then, all right, it says estimate the average velocity. Okay. So we could use the notation they do. That's fine by me. So average rate of change. As long as I don't go too fast here, it looks like it's going to do a pretty good job. All right, that's going to equal the change in the distance, or you could put S here, but I'll use D since that seems to be what they're wanting us to use, over the change in time. Oops. Okay. Come back. Over the change in time. Which in this case, we're talking y's and x's. So the change in y over the change in x. So it looks to me like if we start over here on the right-hand side, old school slope here, it looks like we got 4. So it looks like it ended up at 4. All right. And started at 3. We're talking the y's here. Okay. And the change in time, or the change in x in this case, is 1, 2, 3. So, and again, we could do the same thing we did a minute ago. We could say, all right, we ended up at 4. We started at 1. All right, and so it looks to be 1/3. Yay. Yeah, about. All right, sounds good to me. All right, so, all right, we got another one like that. It says instantaneous. All right, so we've got the speed at a specific instant in time where we're making the difference in the times approach zero. So the instantaneous speed is the slope of the tangent line, so not a secant line. By the way, I don't think I spent enough time talking about that. This is a secant line because it hits more than once. A tangent line is one that hits one single time. So we would want this line. Here, I'll use the shapes again. All right, so we want the slope of that line. Oh, that is just terrible. All right, but let's see if we can make some changes to it. Oh, there we go. All right. Ooh, all right. Pretty good. And I'll just extend it a little bit there. Grab that one. Okay, pretty happy with that. All right, so let's see what we got. Now, so this time we needed a calculus to determine this instantaneous speed, or we could use that method that we used before to see if we could come to a conclusion. But for the time being, sketch the tangent line. Can you estimate? I don't know. It looks like maybe up 2/3, kind of. You see that? I mean, I'm just kind of guessing here. Or just trying to find a good place to count from. My drawing's not exactly perfect, so I'm going to just say it looks like it's close to 2/3. All right, Probably not exactly, but that's a pretty good estimate. So 2/3 seems to be the estimate. And again, I don't believe that's exactly right, but that's pretty close. So they're calling this the IROC, instantaneous rate of change. So I could say that the instantaneous rate of change got some lag at the point where are we at here? 2.4. Is about 2/3. So I'm going to put little squiggles there for approximately 2/3. Okay. All right, that'll work. All right, and we don't know exactly. We'd have to do some additional work to find out exactly what that is, and that'll happen later on in this class. All right, example 2. Have you ever taken a spin class at the gym? Then you know that after the class is over, your rapid heart rate decreases as time passes. Let H of T represent your heart rate. Write an expression for the rate of change of your heart rate over the period T equals 0 to T equals 90. All right, so they're telling us to use H. All right, so let's switch here to red. All right, so my average, the rate of change of your heart rate from 0 to 90. So here's what I need. All right, so I need to know where we ended up. They didn't tell me, but they did tell me the equation we're going to use or the function we're going to use. So I know that that's going to be when time is 90. Okay. All right, and then where did we start? What was our heart rate to begin with? So that would be when time was 0. Okay, so that is the change in your heart rate, but it's over time, literally over time. And that time, of course, was 90 seconds, but just to be consistent, I'll put 90 minus 0. Okay, and then they do one additional step, but you don't have to, or where you just say that it's 90 on the bottom. Okay, so if you want to, we'll do that, and then we are done with example 2. I'm going to have to do something about this lag. It's driving me a little bit crazy, but it's going to be okay. But the good news is, on some of these things that are real slow, you can just move ahead in the video, probably. I would. Oh, Lord of mercy. All right, that's the best we can do. All right, that's it for